our electric circuits example, we have a DC power supply with an ammeter in and 3 resistors. So the first thing it says, students are analyzing this circuit. It's a variable DC, so we can change the amount of voltage coming out. And we are told that R2 and R3 both have a resistance of 50 ohms, but the resistor of R1 is unknown. And students were able to collect the data. The following data shows what the power or potential difference was across the power supply, so 2, 4, 6, 8, 10 volts, and the current in milliamps, 40, 55, 97, 138, 155. On the graph below, it wants us to plot this, so I'm going to pause it and do that very quickly and come right back. Just like that, magic. I've gone ahead and plotted the points, drew the line, labeled my axes. Let's move on to B. It says, using the straight line from part A, calculate the total resistance of the 3 resistor combination. So we are going to use the overwhelmingly powerful equation V equals IR to solve that one out. And what that's going to entail is I is on the y-axis, V is on the x-axis. So ultimately I'm looking for an equation, I equals 1 over R times V. And 1 over R is going to be the slope. So I'm going to calculate the slope and take it from there. So now I know the total resistance of the circuit is 61 ohms. I can go ahead and say that 2 and 3 are series with each other and 1 is parallel to that. So 2 and 3 combined is going to be 100 ohms. Whoops, sorry. Should be plus 1 over 100 equals 1 over 61 ohms. Solving for R1 is going to yield 156. So not to be confused, I'm going to go ahead and separate E and F from D because I don't want you referencing this circuit yet. We haven't gotten there yet. The question is asking, well, what's the current through R2 in this particular branch? So what we can say for the circuit is that this path here is 100 ohms at the full 12 volts, and this pathway here is going to be 61 ohms at the full 12 volts. So let's focus on this right here because this is what we actually care about. We got 100 ohms at 12 volts. Now both 3 and 4 are going to share the same amount of current, which is why I'm using the combined voltage drop of 12 along with the combined resistance of 100. 12 over 100, the current is going to be 0.12 amps. Now we move on to part E. Resistor 3 is replaced with a capacitor and a switch as well. The capacitor is 4 nanofarads and the power supply is going to be once again fixed at 12 volts. It would like to know what is the current in R2 immediately after the switch is closed. So we should assume that the resistance of this immediately after the switch is closed is 0. So let's go ahead and take it from there. This is 61 ohms at 12 volts. This line here, that is 50 ohms at 12 volts because the voltage does not split. V equals IR, so the 12 volts, instead of being across 100 ohms of resistance, is now only across a total of 50 ohms. Total current will be 0.25. A long time after the switch is closed, will the magnitude of the current R2 be greater than, less than, or equal to what we found? Over time, it's going to be less than. What's going to happen is the resistance is going to trend towards infinity, meaning that the current along this branch would plummet to 0. And now it says the capacitor is replaced with a 10 nanofarad. Will the magnitude of current R2 immediately after the switch is closed be greater than, less than, or equal to? It's going to be equal to, because even if this was 10 nanofarads, the initial resistance of it would be 0.